So, in this lecture we start our discussion on the design of certain sequential circuit building blocks. Specifically, we shall be looking at the design of registers and counters, the different types of registers that can be there, different types of counters and some typical applications. So, the title of today's lecture is Design of Registers, the first part. So, let us try to first understand what a register basically means. Look, we have seen what a flip flop is. A flip flop is a storage element which can store one bit of data, but there are many applications where you need to store not just one bit of data, but an entire word of data. That word size can be anything, it can be 8, 16, 32, 64, anything. Suppose I need to store a 16 bit word, then I can use 16 such flip flops to store all those 16 bits of data, and we call it as a register. Register is nothing but an array of flip flops, but how the flip flops are interconnected, that distinguishes the different types of registers. Okay. So, broadly speaking, a register is a group of flip flops. Typically, there is a common clock input, there is a clock input coming from outside which is feeding all the flip flops in that group, and it is used for storing binary data. Now, not only just storing, depending on how you are connecting the flip flops, there can be several different variations of registers. Specifically, registers can be of 4 different types depending on how you are using them: parallel in, parallel out, serial in, serial out, parallel in, serial out and serial in, parallel out. Now, we shall be discussing these variations in due course of time, that what are the main differences and how we can design a register that support these features. Okay. Now, just one thing to remember, if the register is such that either or both of serial in and serial out modes are supported, which means I am talking about one of these three, then we call it a shift register. Shift register is a special kind of a register which supports either serial in or serial out or both of these. Okay. Fine. Now, let us look at these different types of registers one by one. First, the simplest one, a parallel in, parallel out register. I have a group of bits, a word, I just want to store that word in a register, and when required I want to read the value that is stored. So, as you can understand, I can take an array of flip flops. D flip flop will be the simplest, because in D flip flop whatever you give in the input after the clock comes, that will get stored. So, if I have an array of D flip flops, I can very easily implement a parallel in, parallel out or PIPO register. So, the basic PIPO register is shown in this diagram. So, this is a 4 bit register which is shown. You see there are 4 D flip flops we are using. The parallel data input which is coming from outside is fed to the D inputs of this flip flops. These are D 1, D 2, D 3 and D 4. Now, as you can see, the clock input is being fed in parallel to all the flip flops. So, when the clock comes, suppose I have a clock pulse coming like this. So, if it is positive edge triggered, whenever the positive edge of the clock comes, whatever I have given in D 1, D 2, D 3, D 4 will get stored in the flip flop, and they will be available on Q 1, Q 2, Q 3 and Q 4. Okay. This is how it works. Of course, after the clock comes, there will be a small delay. This delay will be determined by the propagation delay of this flip flop. After that the output Q will be changing state, whatever you are applying in D1 will go to Q1 and so on. And this flip flop, as you can see, this also has a clear input which is active low, because this bubble that we are showing here, this means it is active low. Active low means whenever clear is 0, then the flip flops will be cleared. So, if you connect this clear input to all the 4 flip flops, so whenever you want to clear them to all zeros, you can do it. Okay. So, the basic parallel in parallel out shift register works like this. So, as I had said that when the active clock edge arrives, here it is leading edge, rising edge, the input word, this is a 4-bit register, will get stored in the register and will be available on the outputs. So, this PIPO register is very simple in concept, right. Now, a PIPO register can be represented symbolically like this. We do not always have to draw all the 4 flip flops to show that it is a 4-bit register. We simply say that this is a PIPO register, there is a clock input, this symbol is clock, and there is a clear input, again active low symbol is there, and D and Q are shown with vector notation. You see this 4, as you can see here. So, in this line we have made a cross and then we wrote 4 by the side of it. This means actually this is a collection of 4 different lines, not one. So, the number of bits or number of lines I can just represent it like this, and this is called vector notation. So, in vector notation D actually means D1, D2, D3, D4, there are 4 lines, and Q means Q1, Q2, Q3, Q4. Okay. So, this is how symbolically a PIPO register looks like. Now, let us add some features to this PIPO register. Now, the register that we have seen so far, there the data gets stored whenever clock comes. Now, you know clock is a continuous signal, it keeps coming, but all the time I may not be having some data to be stored in the register from outside. So, there should be some kind of a control or facility available to me as a designer, so that I can say that well, now you have to load the data, let the clock come, but whenever I say load, only then you load the data, and at all other times do not disturb the content of the register. Whatever was stored, let it be there. Okay. So, here we are talking about the addition of a load signal. Load signal, what we are saying is that we have a separate signal called load. The idea will be like this: suppose the clock is coming, okay. Let us say this is my clock, and these are the active edges of the clock, rising edge, and suppose this load signal I am giving like this. Suppose I am giving it like this. So, when the first clock edge comes, load is 0. So, there will be no loading. When the second clock edge comes, load is high. So, there will be loading, and when the third clock edge comes, again load is 0, there will be no loading. So, I can selectively specify when I have to load by suitably applying the load signal, but you remember the load has to be made high a little before the clock edge comes, because if you make them high together, then it may not accept the high level of load. Okay. All right. Now, the first approach in which you can use the load signal, you can implement the load signal. There are 2 approaches we shall see. This is something using a gated clock. What do you mean by gated clock? We use an AND gate where both clock and load are ANDed together. So, let the clock come. So, the idea is that the clock signal may be coming continuously, but load may be high only for some time. So, whenever both load and clock are high in the output, only during that time the signal will go high, the other times it will be 0, and this output of the gate will be fed to all the clock inputs of the flip flop. So, that they will be loaded only when required. Now, the issue is that this method may be very simple. You can simply use an AND gate to implement it, but the problem is whenever let us say this load and clock signals are changing at the same time, because you see load is a signal which you are applying from outside. So, accidentally it may happen that you are starting to change the load signal exactly when the clock edge is coming. So, during that time there can be some error in loading or not loading. So, it might get loaded, might not get loaded. So, this solution has a timing issue, there can be a timing problem. If you do not apply the signal in exact timing sequence, there can be an issue. Okay. This can cause timing problems. But let us look at another solution which is better in this respect. Here we are separating out clock and load, we are not combining them using an AND gate like we said. What we are doing here? We are using a multiplexer kind of a circuit. The multiplexer will select what will be applied to the D input of a flip flop. Is it the new data coming from outside or something else? Okay. So, this approach is the better and the recommended solution, as I said, where each flip flop in the register will get replaced by a circuit like this. Just let us try to understand this circuit. Here you have a 2 line to 1 line multiplexer and you have this load control. If load is 0, just try to understand what is happening. If load is 0, which means you are not trying to load. So, whatever is stored in this flip flop should remain. So, in a register there will be a number of such flip flops. Okay? I am just showing one flip flop, but the clock is coming continuously. Okay? So, whatever is in D will anyway get loaded with every clock. So, when load is 0, what I do, whatever is getting stored, I select that this will be my 0 input of the multiplexer when load is 0. This Q1 will get selected and come to D. So, the same value will get stored, same value will get stored. So, no change. But when load equal to 1, I want to load the external data D1 which is coming. So, this will be my 1 input of the multiplexer. When load is 1, D1 will come in and D1 will get stored. Okay? So, this is a very simple approach, this you can use, and a register which has this kind of facility can be represented schematically just very similar to the previous one with the addition of an extra input called load. So, clock is there, clear is there, but in addition there is a load. So, whenever this clock is coming, depending on the value of the load, either the same value will get loaded or the external value will get loaded. Okay. Now, there is another kind of a input which is required in many applications, as we shall see very shortly. This is the so called enable input. The idea is as follows. I have a register. The register output lines will be giving me some data, the data that is stored in the register, but there are applications where I want to sometimes electrically isolate the outputs. Electrically isolate means I want to send them to the high impedance or tri-state. So, there can be a separate enable input to the register also, where if I enable the register, only then the outputs will come, but if I do not enable, the outputs will be in the high impedance state. Okay. This is the idea. So, as you can see, it says that using the enable input, register outputs can be put in the high impedance state. but for this you need some kind of a tri-state buffer connected to every flip flop output. So, I am showing the schematic here for one flip flop again. Suppose I have one flip flop of the register, the output instead of directly sending to Q1, here we are using a tri-state buffer. This is a tri-state buffer. Tri-state buffer, what it does, if your enable is 1, that means you are enabling it, then the output Q1 will be getting whatever is there in Q. This is the normal mode of operation. But if you are not enabling it, enable equal to 0, then this output Q1 will be in the high impedance state, we denote it as Z. So, it is electrically isolated. Okay? This is the idea behind the enable. Now, let us take a concrete example where this kind of enable input is actually required. Now, there are numerous examples where you do not have a single register, but many registers. You can take the data from any one of the registers and you want to send it over a common bus to some other place. So, you may need to tie the output of several registers together, but in a normal circuit you just cannot tie them together, right. Let us say if one of the output is 1, other output is 0, if you tie them together there will be a short circuit and a high current may be flowing and the logic level may be either 0 or 1 or something in between. So, there can be some error. So, in a similar situation, when you have a bus based architecture which is very common in computer systems, in microprocessors and computer systems, we can use the enable input to resolve bus conflicts. So, I am showing a very simple example scenario. Just look at this. Here this RA, RB, RC and RD, these are all k bit registers. They are storing k bit numbers, k can be anything 8, 16, 32, 64 anything. Now, you see these 3 registers A, B, C have separate enable inputs, enable A, enable B and enable C, and the output of these registers I am tying them together. Well, actually what do you mean by tying them together? Let us say in the first register, let us say k equal to 3, this is RA, let us say this is RB, I am showing only for RA and RB, these are the 3. Tying them together means the first output of RA and the first output of RB I am tying together, second output of RA and the second output of RB I am tying together, and third output of RA and third output of RB I am tying together. Similarly, for RC. Okay. So, these were k bit registers. So, the output what you get is also a k bit output, 3 outputs are coming, right. So, you see these registers have k bit outputs, after tying together you have a k bit number. Then I have another register RD and there is an adder. Now, in this adder, one of the input is coming from one of these registers and the other input is coming from RD, and the output of the adder is going to RD. Now, here I am assuming that exactly one of the 3 enable inputs can be active at a time, exactly one, enable A, enable B, enable C. So, you will be making one of, let us say I want to enable RA, I make this as 1, I make these two 0 0, exactly one of them will be 1, and clock is being fed to all the registers in parallel. So, what will happen? If enable A is active, then the output of RA will be coming here, because RA and RB are electrically disconnected, they are in the high impedance state. So, RA will be coming to this adder input and the other input is RD. So, RD will be getting added to RA and the result will be stored in RD. Similarly, if enable B is 1, then RB will get added, and if enable C is 1, then RC is getting added. So, here I have shown you a very simple example but in practical scenario there can be numerous such examples of data coming from various places and you want to combine them and send them over a single common bus. Here this common line that I am showing here, this is called a bus. 3 registers are feeding their data to a common bus, right. So, this is an example where this enable signal of the register can be very useful. Okay. So, we have seen that how we can implement flip flops using gates. Gates can be implemented using any kind of technology. Okay. We talked about TTL, CMOS and some other technologies as well. Now, specifically let us now look at how we can implement registers using CMOS logic, because most of the circuits that are designed today are built using CMOS and there are some very simple tricks that you can use in CMOS design to reduce the complexity of the circuits. Okay, let us see how. Now, what we are talking about here is how we can implement a PIPO register using CMOS by using something called dynamic logic. So, what is the idea behind dynamic logic? Well, you all must have heard about the dynamic memories in computer systems. So, the memory that comes with the computer systems are almost universally they are dynamic in nature. Dynamic memory is based on a very similar principle that we are going to discuss now, dynamic logic. So, in dynamic storage, we store information not in flip flops, but as charge stored on tiny capacitors. But where are these capacitors coming from? Let us take a very specific example. Let us talk about a NOT gate connected like this. This is a CMOS NOT gate. So, how does a CMOS gate looks like? If you recall, there are 2 transistors, one is a p type transistor, one is an n type transistor, they are connected together. This is your input and from this common point you take the output. This is your power supply VDD and this is your ground. Now, if you look at this point, this line is being feeding to the gate inputs of 2 transistors. Now, for those of you who know how a transistor is fabricated, there is a substrate and the gate is formed on top of the substrate like this, and there is an insulating region here, and the substrate is typically connected to ground. So, you see this looks like a parallel plate capacitor. There is one terminal this side, one terminal this side and insulating region in between. So, as an equivalent circuit I can say that well as if it is driving a capacitance. So, when the input I am changing from 0 to 1 as if I am charging this capacitance, and when I am changing it from 1 to 0 as if I am discharging the capacitance. Now, the idea behind CMOS dynamic logic is that well by either charging or discharging capacitance I can store 0 or 1 there, and you know a capacitor has a capacity to store some charge for certain point in time. So, once I charge a capacitor to some required voltage either high or ground representing 1 and 0, then it will retain that charge for certain amount of time. Of course, the charges will slowly tend to leak away. This is not a permanent kind of a storage as you see in a flip flop, where as long as power supply is there the data will get stored, but here data will remain for a short duration of time which is of the order of milliseconds. Now, in terms of the circuit speeds today, milliseconds is a very large time. Okay. So, the charge you are storing on the capacitor can be retained for this period of time, after which they will tend to decay or dissipate. This is the basic idea behind dynamic storage. So, charge tends to leak away with time, and we need to refresh the charge if you want to store it. So, let us see how we can implement a simple register using dynamic logic. This is a register where each of these rows represent one flip flop or equivalent of one flip flop. So, you see my data input is coming here, my final storage output is coming there. This X is a CMOS transmission gate. So, when clock or load I am setting it to 1, so this gate is open, and you see here after this X there are two inverters, right, connected one after the other. So, I am interested in the capacitor here. So, when this gate is open, when this control of this transmission gate I am setting to 1. So, whatever I had applied on D 1 or 0, that voltage will get charged on the capacitor, and after it again comes back to 0. So, this transmission gate again closes. So, this capacitor does not have any path to discharge, but of course, there will be some leakage path, very slowly it will discharge, but the data will get stored in the capacitor, and there are two inverters because whatever you are storing there, the same value I want here. So, two inversions will cancel each other. Okay. So, this is a simple storage. So, if you want a k bit register, there will be k such D 1, D 2 to D k, right. This is a very simple PIPO register using CMOS dynamic logic. Now, if you want to also add tri-state control as we had discussed for normal registers earlier, what you can do, we can add another set of transmission gates on the output side and we connect them to enable. So, if enable is 1, then this transmission gates will be enabled and this output of the NOT gate will come to Q 1 or Q k, but if it is not enabled, then the outputs will be in the high impedance states. Simple. So, you see for a normal conventional design, we have to use gates, construct flip flops, D flip flop, master slave flip flop, so many gates are required, but here you see the design is so simple. Here in CMOS technology, every inverter requires 2 transistors, 2 plus 2 4, a transmission gate requires 2 transistors and a 2. So, a total of 8 transistors are required to implement a register with tri-state control, a single bit register. Okay. But now, the question comes that these charges tend to decay or dissipate. How do you refresh the charge? Okay. Because we want to store some data over longer periods of time. So, there are simple ways available for this. Here we are showing one possible solution, and we are showing again for a single flip flop stage. So, here we have our flip flop as we have already discussed earlier. There is a clock or load control and there is a tri-state enable control. This is something we are adding. There is another transmission gate we are adding here, which is been fed with the knot of clock. You see clock is coming like this. So, if I say knot of clock, so it will be just knot of this. So, when clock is high, this gate is open and whatever there is a D 1 it gets stored as charge on this capacitor which is here, right. But when clock is 0, this region, when clock is 0, new data is not getting stored, but this transmission gate is now open because this is activated by clock bar is high. So, what will happen? Whatever is stored in the output of the second NOT gate, that comes back to the input of the first NOT gate and it recharges the capacitor. So, if it was 1, this will be 0, this will also be 1, this 1 is fed back, that same value gets charged, and if it is 0, that same 0 will be fed back. So, in this way, in every clock cycle, for every clock period when clock equal to 0, the data is getting automatically refreshed. right. So, by the addition of another 2 transistors we can also have this refresh mechanism. So, with this we come to the end of this lecture, where we have discussed the design of simple parallel in parallel out registers, and we talked about the different kind of inputs that may be useful like load and enable, and specifically we looked at how to design a PIPO register using CMOS dynamic logic. Thank you.